In today's lesson, we discuss multicast routing and its foundation, broadcast. Previously, we discussed many routing mechanisms that assume a given source transmits its packets to a single destination. But in some circumstances, such as teleconferencing, a source may want to send packets to multiple destinations simultaneously. This calls for another type of routing called multicast. As illustrated in the figure, source S wants to transmit to destinations with multicast group G1. Though it can send each copy of the packet separately to each destination using conventional unicast routing. A more efficient method would be to minimize the number of copies. For example, when router 1 receives a packet from the source, it copies the packet to routers 2 and 5 simultaneously. Upon receipt of these packets, router 2 forwards the packets to its local network, and router 5 copies the packets to routers 7 and 8. The packets will eventually be received by each intended destination. There are many ways to generate a multicast tree. One approach that is used in multicast backbone is called reverse path multicasting. The easiest way to understand reverse path multicasting is by first considering a simpler approach called reverse path broadcasting, which uses the fact that the set of shortest paths to a node forms a shortest path tree that spans the network. Assuming that each router already knows the current shortest path to a given destination, the operation of reverse path broadcasting is quite simple. Upon receipt of a multicast packet, a router first records the source address of the packet and the port it arrives on. If the shortest path from the router back to the source is through the same port we call parent port the packet arrives on, the router forwards the packet to all other ports except the one packet arrived on. Otherwise, the router drops the packet. The advantage of this approach is that each packet is forwarded a router exactly once. The basic assumption underlying the algorithm is that the shortest path from the source to a given router must be the same as the shortest path from the router back to the source. This assumption requires each link to be symmetric. Let's see an example. The port over which the router expects to receive multicast packets from a given source is referred to as the parent port. The figure shows the spanning tree of shortest paths to node S, and the parent ports are shown in color red. First, router 1 received a packet on port 1 from source S. Because the packet comes from the parent port, the router copies the packet to all other ports. Assume these packets reach routers 2, 3, 4, and 5. Router 2 computes the shortest path from itself to S and finds that the parent port is 1. Due to the match, it copies the packet through all its other ports. Similarly, routers 3, 4, and 5 find that the packet arrives on the parent ports. As a result, each router copies the packet to its other ports, as shown in the figure. Note that the bidirectional link indicates that each router forwards a packet to the other. Next, let's assume that the packets arrive at routers 2, 3, 8. Because route 2 receives the packet from port 4, which is not its parent port, router 2 drops the packet. Routers 3, 4, and 5 also drop the packets for the same reason. Router 6 however, finds that the parent port is port 1, so it copies the packet coming from router 4 to its other ports. The packet came from router 5 to router 6 is dropped. Router 7 and 8 copy the packet that came from router 5 and forward to other ports. The figure illustrates this process. Please verify that the packet will no longer be propagated after this point. Note that although the hosts connected to router 3 and 6 belong to different multicast groups, the packets for group G1 are still forwarded by these routers. Unnecessary bandwidth is wasted regardless of the multicast group. This problem can be solved by having the router truncate its transmission to the local network if none of the hosts attached to the network belong to the multicast group. This refinement is called truncated reverse path broadcasting. The Internet Group Management Protocol, IGMP, allows a host to signal its multicast group membership to its attached router. A multicast router periodically issues an IGMP query message to check whether there are hosts belonging to multicast groups. Routers determine which multicast groups are associated. Routers determine which multicast groups are associated with a certain port. Routers only forward packets on ports that have hosts belonging to the multicast group. Briefly speaking, reverse path multicasting is an enhancement of truncated reverse path broadcasting. But unlike truncated reverse path broadcasting, reverse path multicasting forwards a multicast packet only to a router that will lead to a leave router with group members. To do so, it relies on IGMP to identify multicast group memberships.